Welcome back to my channel, everyone. My name is Ansar, your helping hand, and today we're going to continue our discussion about the normal approximation to the binomial, and specifically in this video we're going to look at how exactly we use this approximation to calculate probabilities, and we're going to talk about something called the continuity correction, which makes our approximations a lot better. So just a quick recap from the last video as to why we can use this approximation. And basically we can do it because the central limit theorem says that as our n increases, our binomial looks more like a normal. And so the important thing is that because this starts to look like a normal, we can approximate our x with a normal, and we know that calculating probabilities on a normal distribution is very easy because if you standardize it, you get a standard normal, and you can just go and look up those probabilities in a table. Okay, so for this video, we're just going to kind of go through how we go about finding probabilities using this approximation and what they look like and how we make them better approximations. Yeah, okay, cool. So we're going to try and find the following probabilities, and this is our binomial distribution where there's 80 trials and 0.4 is our probability of success. So it's not exactly 0.5, so it's not exactly symmetrical, but because it's close to 0.5 and our n is quite large, we can actually use the normal approximation, and we'll see how well it fares in terms of calculating these specific probabilities. Okay, so our first probability is we're looking for the probability that x is greater than or equal to 36, right? Now, if we take a look at our binomial distribution, this is the PMF right over here. This is the PMF of the binomial, and essentially we are looking at, we're adding up all of these areas of here. Sorry, this orange is not really registering on the pink, but we're adding up this area for 36, 37, 38, 39, all the way up until 80, and this graph doesn't go to 80, it just goes up to 46. But you can see that all of those areas, once we sum them all up, that will be equal to the probability that x is greater than 36. Now, obviously, we can go and we can, figure out this probability exactly, right? All we have to do is sum from I equals 36 all the way to 80, and we sum up these areas, and these areas obviously are the PMF of a binomial, and we can go and calculate that exact answer, and it's 0.215. Now let's see what happens when we use our normal approximation, right? When we think about our x as being a normal rather than a binomial, this is the case that we have. So we have this binomial, right? The PMF of the binomial is kind of in the background, and we have this normal distribution that's kind of overlaid on top of it, right? So the probability that x is greater than 36 is, well, we're taking x to be a some normal, so we're putting down our bound here at 36, and then we're basically calculating the area to the left of that, and that's under the black curve, which is the normal curve. So we can go and do that, right? But before we go and do that, we kind of want to standardize it because it's a lot easier to work with standard normals than it is to work with non-standard normals. So we subtract our mean, we divide by our standard deviation, which is the square root of the variance over here. And remember, these numbers come from NP. If you take 80 times 4, you're going to get the mean, and 19.2 is NPQ. So that's the variance of a binomial. Okay, so we've standardized our normal approximation, right? And we can say, okay, cool, the probability that x is greater than 36 is the same thing as, well, I'm going to standardize my x over here. So I'm going to subtract 32 and divide by the square root of 19.2, and I'm going to do the exact same thing on the other side. And then, that's going to be the probability that some standard normal is greater than a particular amount. And we get this answer from a table or from a calculator or from RStudio or whatever statistical software package you want to use, or however you get your normal probabilities, right? So we can see, right, 0.215 and 0.1806. It's not exactly equal, but it's an approximation, so it's kind of okay. Like it's near each other, which is, I guess, what you want approximations to be like. Okay, so that's the greater than or equal to 36. Okay, now we're going to do when x is just greater than 36. Okay, so in that case, we're no longer including this little bar over here, sorry, the 36 bar. We're just including 37, 38, 39, all the way up to 80. we can go and do that, go and calculate that using, either a computer or your calculator, if you have a calculator that can do sums, or you can do this by hand. It's going to be very tiring, but you can do it, and you get to 0.1523, right? And then if we do the same thing with the normal, right? Remember, for x is greater than 36, we have this normal distribution, okay? And we're saying our bound is at 36, and then we're saying basically because it's greater than, we're doing all the area to the right. Sorry, I think I said left earlier, but we're doing all the area to the right as well. Now, you can see that in the normal case, because we're using a continuous distribution, in probability terms, greater than or equal to and greater than are equivalent when we calculate probability. So we're not going to get anything different. We standardize it in exactly the same way, and we get the exact same answer of 0.1806. So we can see again, okay, it's not a great approximation, but obviously doing this calculation with a normal, right? Doing this calculation is a lot easier than doing, how many is that? That's 43 binomial. It's a lot easier than doing 43 binomial calculations and adding them all up. So you kind of have this trade-off of being like, okay, do I want to do 43 binomial calculations, or do I just want to do one calculation for a normal? And you have this trade-off between, okay, this is the exact answer and this is the approximate answer. Okay, so that's greater than or equal to 36, and I'm just going to kind of zoom through the less thans, right? When you're doing less than, we're obviously adding up all the values less than 36, so we're going that way now to the left, and we're including 36 because there's a less than or equal to sign there. So we go and do that, we go and calculate it, and it comes out to 0.8477. We can do the same thing with the normal, except now our bound is still at 36, but we're now calculating all the area to the left of the bound. So now we can do the exact same thing that we did before, standardize our normal, calculate the probability that x is less than or equal to 36 is the same thing as some normal being less than or equal to 36 minus 32 over root 19.2, and that's the probability that some normal is less than this particular number. And we get 0.8193. So once again, we've got the first digit correct, or the first decimal place correct, and it's not exactly equal, and it's not really close after the first decimal point. But once again, here we're looking at doing 36 different calculations, and here we're looking at doing one calculation. So you kind of have to pick your battles, right? In an exam or in a test, you don't want to calculate 36 different binomials, but it's a lot easier to calculate one normal probability. So that's the less than or equal to, and then for the less than, it's almost identical, except we're no longer including 36. And so we can get the probability for the binomial, the exact probability, and that's 0.7885. And then for the normal, we're going to have the same kind of, not instantly issue, but we're going to have the same behavior as we had last time with the greater than or equal to versus the greater than, which is that for a continuous distribution, less than or equal to is equivalent to less than. So it's going to be, it's going to be the exact same thing, standardize our normal, and calculate the probability that x is less than 36. We standardize 36, and we're going to get the exact same probability of 0.8193. So this is just a table of our approximation results that I'm going to show you now. So we had each of our events, and then we had the exact probability and the approximate probability using the normal distribution. And we can see here that for some of them we kind of undershoot, and for some of them we overshoot. And you'll notice that the undershooting always happens when you have a non-strict inequality, so when you have an equal to as well, right? And the overshooting happens when you have a strict inequality. So these approximations, once again, are not very close. So like, for instance, here we've only got the first digit. And then for the rest of them, here we also kind of have the first digit. So we have 2 digits, I guess, of accuracy out of That's 4 times 4. We have 2 out of 16, basically, digits of accuracy, which is not great. But like I said before, it's, that's that kind of trade-off between having to calculate multiple binomial probabilities versus one normal probability. So there is that kind of trade-off. And the other thing that we can see, as I said earlier, is that there's the systematic over or undershooting. So what I mean by systematic over or undershooting is that anytime you have a greater than or equal to sign, and anytime you have a less than or equal to sign, anytime you have the equal to inside your inequality, you will always undershoot. And anytime you have a strict inequality, right, when you don't have the equals to sign, you will have you will overshoot, basically. So that's a systematic issue within the approximation, right? And this would be present for any probabilities found using this approximation. And so there's this kind of like, yeah, it's not great, and we kind of want to figure out why there is this issue. And if you were paying close attention to the probabilities earlier, or the graphs that I was showing, you'll see that the reason for this is because essentially this approximation issue is due to a continuity issue. We're using a continuous distribution to approximate something that's discrete. So what I mean by that is that in this particular thing over here, we can see that when we choose 36 as our kind of bound of interest, right? When we do an exact probability, we include all of this pink area as well, right? And when we're using the normal approximation, we're looking at the green area, and the green area will always be less than, will always not include this pink area in this case, or sometimes it will be more than the pink area. If, for instance, we were taking greater than without the equal to, then we would just be taking 37 onwards, and then we'd have this like kind of little green overhang over here. So we can see that the normal distribution kind of works, but because it's a continuous distribution and the binomial is discrete, we have this continuity issue. So we can actually correct for that. We can actually correct for this and get a better approximation. So I'm going to explain what the correction looks like. And basically what we're going to do is, in every single case, we're going to look at, are we overshooting or undershooting, and how exactly do we go about correcting it? And that's either going to be adding a little bit here or subtracting a little bit, and we'll see what it looks like in each example. Okay, so in the greater than or equal to example, right, this is the exact probability we have over here using the binomial calculation, right? And over here we have our bad approximation. Now, in our bad approximation, the issue is that the pink area is the area we want, and this green area, because we're starting it at 36, right? Because we're starting it at 36, we're not really getting all of this other pink area over here, and that pink area is included in the binomial probability, so we do need to include it in the normal. So we can go, okay, well, if we want to do 36 and we want to do that it's greater than, right? Remember the non-strict inequalities, the inequalities that have an equal to sign, right, in them, they were always undershooting. So we need to add probability, basically. We need to add this pink area to our probability. And when we're doing a greater than comparison, right, adding a probability means subtracting our bound, right? Subtracting something from our bound. So basically making our bound go here. And that little subtraction, right, we can, the exact value of that subtraction is just 0.5 because it's in between 35 and 36, which is going to be 35.5. So we can see here that when we do it at 35.5, right? When we do it at 35.5, we get a much better approximation. Suddenly, there's no longer this big pink area that we're not considering, right? So what we're basically saying is that when we think of our probability as being greater than or equal to 36, right, in a normal situation, right, that's approximately, and now this approximately is not an approximation thing. It's basically, we're saying, okay, instead of doing it at 36, I'm going to do it at a little bit less than 36, and those two, that value and that value, should be close to one another. That's what that approximation means. But in the context of normal approximations to the binomials, this probability is going to be a lot closer to our actual exact probability. So we can go and do the same exact thing we did with the earlier examples where we standardized it and say, okay, that means x minus 32 divided by square root of 19.2, and we standardize the 35 because 36 minus 0.5 is 35.5. And now it's that this standard normal is greater than 0.7988. And when you go and calculate that probability using a table or statistical software or calculator or whatever you use, you'll see that it's equal to 0.2122. So this is a much better approximation. It's got 2 digits of accuracy rather than 0 in the first case, right? So this is a much better approximation with the continuity correction. So the continuity correction is this adding or subtracting 0.5. We subtracted in this case, but we'll see sometimes we add, sometimes we subtract, and there's a kind of way to go about thinking about it. Okay, so this was the greater than or equal to case. Now we're going to go to the greater than case. And I just want to quickly remind you of the understanding is that when you have the equality part of your, basically the equality part, the equal to sign in your inequality, then you're going to be constantly undershooting your probability with your normal approximation. And when you have just the greater than or just the less than, you're going to be overshooting. So here we can see that when we're doing just greater than 36, in the binomial case, we're just adding up this probability and this probability and that probability and that probability and all of those. But when we use our normal approximation, we're adding this extra green area over here that we don't actually need. So essentially, we have overshot our probability. So in order to correct that, we need to remove some probability, right? In the previous case, we needed to add because we undershot. Here, we need to remove because we overshot. And because we're doing a greater than comparison, removing probabilities when we're doing a greater than comparison means adding something to our bound, right? Or pushing our bound to the right, or pushing our bound away from the mean. Okay, so here we can see what it looks like when we have our continuity correction. So instead of looking at 36, right, instead of our bound being 36, we're adding some little amount, and it's always going to be 0.5 because it's always just the average between two bound values, right? So we're adding 0.5 to get to 36.5, and this area over here no longer has this systematic overshooting, right? Systematic because it's always going to do that, right? And you can, I wanted to say something, but it's not really important. So we can once again go and do the same process of going, okay, you know, this probability that x is greater than or equal to, greater than 36, right, is, and it's the same case as before, this approximately means that being greater than 36 is going to be close to being greater than 36.5, right? That's what this approximation means in the sense of the actual probabilities that we calculate for these using the normal distribution. Those are going to be close to one another, but in the context of normal approximations to the binomial, this probability over here is going to be a lot closer to that one, and we can go and do it. We go and say, okay, so we standardize everything, and we see that we're looking at z is greater than 1.0270, and if you look at that, you've got 1.522, and so now we've suddenly gotten 3 degrees of accuracy, as opposed to none in the first bad approximation or the overshooting version. Okay, so you can see that doing this continuity correction makes sense, right? And it always makes our approximation better. And we can go and look at what it looks like in the next case. So once again, I'm just going to zoom through the basic important parts, right? So because we have a non-strict inequality, right? We saw earlier that overshoots our probability. A strict inequality undershoots our probability, and we can see that here with this pink area thing over here. So we're not adding this pink area thing. So we need to somehow correct our undershot probability by probability, and adding probability when we're talking about less than symbols or less than inequalities means subtracting our bound, right? It's pushing our bound inwards or more to the left. Yeah, I think I said right earlier. Sorry, I may have been slightly dyslexic with regards to where I'm going, right or left. But yeah, so you can see that at 36, right, we have this. Oh, I've completely messed that up now. Sorry. So let me just kind of reiterate everything from the beginning, right? Less than or equal to, because it's got an equal to, right, will always undershoot probabilities, whether it's less than or equal to or greater than or equal to. Because it has the equal to in the inequality, your probabilities will always be undershot. So we need to add more probability to it. So we need to account for this little pink area over here, and adding probability in the case of less than symbols means adding 0.5 to our bound, or pushing our bound to the right, or pushing our bound away from the mean so that we can add more probability. Okay, and we need to add more probability because we've undershot. So if we go and do that, we can see, okay, this is what it looks like. We're instead of looking at 36 as our bound, we're going to look at 36.5 as our bound, and we're adding 0.5, and we standardize in the exact same way, and we see, okay, the probability that z is less than this particular 1.0270 is 0.8479, and once again we've gotten three decimal places of accuracy versus 1. So it is, we can see that it is, the continuity correction helps us, and that we should continue to do it. And just the last one, where we're less than 36. So the less than, because it's a strict inequality, it overshoots our probability. We're adding this green area here where we shouldn't be. So we need to subtract that green area. And in the context of subtracting areas with a less than symbol means moving our bound to the left, or subtracting from our bound, or pushing our bound closer to the mean, however you want to think about it. So we can see that this is what it looks like when we do the continuity correction. Instead of looking at 36, we're looking at 35.5, and we do the exact same thing. You know, these probabilities are approximate in the sense that they're close to each other on the normal, so they will be close to each other, but this continuity corrected version will be a lot closer to our exact probability. So we go and standardize it. We go and find that our bound in the standard normal case is 0.7988. And we go and calculate it, and we see, okay, 0.7988, that is that probability with a standard normal is 0.878. So now we've gotten 2 degrees of, or 2 decimal places of accuracy, rather than 0 in the bad approximation case. So we've obviously seen that the continuity correction, right, this good approximation, the one with the continuity correction, that's a lot better, right? It's a lot better. It's closer to our exact probability, right? 0.211 versus 0.21 than our bad approximation. Okay, so our good approximation will always be, or the continuity corrected version of your approximation will always be better than the non-corrected version. And we can see what we had to do in order to figure out that correction, right? And so we can see that the continuity correction always made our approximations better, and this will always be the case, right? If you correct your bounds using the continuity correction, doing a normal approximation makes a lot more sense than when you don't do it, and it makes it a lot easier, or more accurate, actually. It doesn't make it easier because you have to think about how do you correct for this continuity correction. So you can go and memorize the case, or like I was kind of stressing throughout the whole process, is you can understand the rules. So when we're talking about strict inequality, right, our correction needs to remove probabilities, right? And by correction, I mean we're either adding or subtracting 0.5, right? And the reason we need to remove probability is because without the correction, we overshot our probability, we overshot the area, and so we need to remove some kind of probability, we need to remove some kind of area. And so when we're talking about removing probability, right, when we're doing a greater than comparison, if we look at this kind of a case, right, if we're talking about this is our bound here, x, and this is the area we want, right? We need to kind of, when we're removing probability, we need to move our bound to the right-hand side, right? And that is the correct side. We need to remove it. We need to move our bound to the right-hand side. So we need to push our bound to the right. We need to push our bound outwards. If you are, if you are on the other side of the mean, it's outwards, or further away from the mean. And in this case, it doesn't really, further away from the mean only makes sense if your bound is already on the, if your bound is already greater than your mean. But I just added these things so you can think about how you need to go about, thinking about whether I'm adding 0.5 or subtracting 0.5. And then here, when we're talking about a less than probability, right? If we're talking about a less than probability, this is the probability we get with any particular bound, right? We need to remove probability because it's a strict inequality. We're just looking at less than. So removing it means pushing it to the left, right? So pushing it here somehow. And by pushing it to the left, you're doing a subtraction from your bound, okay? And then for non-strict inequalities, right, our correction, our plus or minus 0.5, we need to add probability because without it we undershot. And so therefore, when we're doing a less than, right, so if we have this case over here where we have x is here and this is the greater than, right, this is the greater than or equal to, because we need to add probability, right, if we move our bound to the right hand side, we're going to subtract probability, so we need to move it to the left, right? And essentially, when your bound is on the right-hand side of your mean, right, there's mu for whatever reason, if your bound is on the right-hand side of the mean, right, adding probability means moving your bound closer to the mean. So that's why you subtract 0.5 when you're doing a greater than or equal to comparison, and the opposite for the plus 0.5. So these are just the rules for the continuity correction. You can... One way that I like to think about it is that if you have a strict inequality, right, your inequality tells you the direction you need to add or you need to go. So because it's pointing to the right-hand side, you need to go to your bound needs to go to the right-hand side, so you're adding. And then when you are doing a less than or equal to comparison, it's pointing to the left-hand side, so we need to push our bound to the left-hand side. And that usually means subtraction, or that always means subtraction. And then in the non-strict inequality case, when you've got the equal to, it's just the reverse. So I kind of think, okay, if we're doing a strict version, this thing says it's strict. It means it's very important. It's saying it's a strict inequality. So that kind of reminds me that the strict inequality means we look at the direction that our strict inequality tells us to go. And when we're doing a non-strict inequality, you can kind of think, okay, I can be a bit more loosey-goosey, and therefore that means I'm going to do the opposite of what it says. So yeah, that's been the continuity correction and how we use the binomial or the normal approximation to the binomial. That's the end of this particular video. Please don't forget to like and subscribe, comment if you have any questions or requests. And then I will be having some more real world questions where I take exam questions and go through them. So I'll have a link to that as well, so you can watch those. And yeah.